This video is part of a course on food physics, of which this is the theory section. This subsection belongs to the governing equation for heat transfer. The immediately preceding video is an overview of transport processes, and the immediate follow-up video is the derivation of equations for mass transfer. Now the equations here are complete and they are derived from scratch, but they're not meant to be a replacement for a course on transport processes. So the heat equation that we will derive is simply a mathematical statement of conservation of thermal energy that we are all familiar with. But to apply this thermal energy conservation to let me write that. So the conservation just says in minus out plus generated should be change in storage. But to apply this to a physical system, we first have to define the system boundary. It can be totally arbitrary, a food product, part of a food product, a equipment, and even bigger scale. But once I define this boundary here, this is my boundary, then I apply this conservation principle that says energy coming in minus energy going out plus energy generated should be equal to the change in the energy storage. Now a little bit more details of those terms in the previous slide. One of those was heat generation. So heat generation, what is the meaning of heat generation? It's really conversion from other forms of energy to thermal energy or change of phase. So let's look at two examples. And one is microwave heating. So in microwave heating, it's a positive heat generation, but what is that due to? It's simply because electromagnetic energy is being converted to thermal energy. Another example of heat generation, let's say when we are doing bread baking, then we have evaporation inside the food. So if water changes from liquid to vapor, then it's taking away some of the heat. So it's a negative generation and it's happening because of latent heat. So these are just two of many examples of what we mean by the heat generation term. Back to this conservation slide. So we just talked about heat generation, and then we want to talk about the in and the out terms. And the in and out terms are thought in terms of fluxes of energy coming in or going out. So how do we write those fluxes? Here is how we write those fluxes. So imagine a gas that has some hot ones, hot molecules, the red ones, and some blue ones that are colder, and they're moving randomly. So there's heat conduction when they're touching, and that heat flux is the conductive heat flux given by Fourier's law, minus k del T del x. So if we think of this imaginary line, like this blue line here, then heat crossing this line into this direction by conduction alone would be given by this term. And if we look at the units, it's a flux because K, the thermal conductivity unit, is watts per meter per degrees Kelvin, and del T del X is degrees Kelvin per unit distance. And so that gives me joules per meter square per second. So it is a flux, energy, joules per unit area per unit time. But this conduction isn't the only possibility. This entire gas can move. There can be bulk flow, like you see here. So how do we bring in that flux? That is on top of the conduction flux. And how much is that? It is the convective flux is given by the velocity, the bulk velocity, times the energy content. So let's look at the units. Rho CPT, if we look at the units, it's kilograms per meter cube density, and Cp, specific heat, is joules per kilogram per degrees Kelvin times degrees Kelvin. So we cross out these and we get joules per meter cube. So this is the energy content, and this energy content is simply moving due to bulk flow. So this joules per meter cube is moving with the velocity meters per second, and if you multiply, you again get joules per meter square per second, just like this term. So they can be added together. So then we have two ways that energy can come into or go out of the control volume: conduction and due to flow. We are now ready to apply the conservation principle to an arbitrary control volume and derive the energy conservation equation. So then our statement, the word statement, is energy in minus energy out plus energy generation equal to change in energy storage. So we choose an arbitrary control volume. This is nothing special about this. It's just a control volume of size delta x, delta y, delta z, through which it's a fixed location in space, and through which energy, like the example I gave, if it's gas, energy would be coming in through conduction, which is a diffusive type process, or convection. Now conductive flux is given by minus k del T del x, and convective, or the flux due to flow, is given by U rho Cp, and here it's written in terms of T minus Tr, which is a reference temperature, a constant. So since that will cancel out later anyway, we can drop that one. So it's just U rho Cp T. So the fluxes are the conductive flux. Let's just call it conductive flux. Diffusive is not wrong. Conductive flux is minus k del T del x, and convective flux is U rho Cpt, as we just derived in previous slide. And so together they will be coming in. This is the total. They will be coming in, and the same for going out. Okay. And so how do I now apply this conservation law for this situation? So we have to write each term at a time. So so this is the total amount of energy. So minus k del T del x plus U rho Cp T at the location x. So here, so at that location, that's the rate at which energy is coming in. So if we put in units of this term, it would be joules per meter square per second. Okay, and this is coming over this cross-sectional area of the cube on the side that we're not able to see. So that is delta y, delta z. So that would be the area. And then if we do the energy balance over time delta t, so that's seconds. And so this would be then joules of energy that comes in. And in the exact same way, I can write the joules that are going out, which has identical terms, but at the location here. So this time, okay, here, times the same area and time. Now, energy would be going in and out through other phases as well, this one and this one, but we are doing a 1D situation, 1D balance, just to keep our life easy, and also more importantly, we can easily interpret those terms more easily. Okay, so we're doing a 1D case. So then we did in, out. Next one is generation. So generation, as I showed you, like in microwave heating, generation term Q has the unit watts per meter cube. So that is joules per meter cube per second. So it needs to be multiplied for this entire control volume. This is my control volume. For the entire control volume, then the heat generated would be this multiplied by del x, del y, del z meter cube times second. So then again, this would be joules generated. And because of energy coming in, going out, and generation, there's going to be some change in the storage, or there can be some change in the storage. So what is change in storage? Change in storage, if it stores more energy, that means its temperature will go up, right? So then change in storage is simply measured by the change in temperature. And so the heat content of a mass is mCpT, mass times specific heat times the temperature. So the change in storage is the change in this quantity. So since the mass and specific heat are not changing in our example now, then it is the T that is changing. So it's delta T times mass is delta X, delta Y, delta Z, that's the volume, times the density, and times the specific heat. So this is joules storage change. Okay? And so with that, we can now simplify. So we divide throughout by delta X, delta Y, delta Z, delta T throughout to get the next equation. So let's look at these terms carefully. So let's say this guy, when I divide by delta X, delta Y, delta Z, delta T, then I get rho Cp del T del T. That's what this term is. Okay? Still with me? Then the next term is I collect the terms that have U. So one here and one here. So then this one gives me ut del x, x plus del x, and this term gives me ut at x. So difference between them divided by this again delta x, delta y, delta z, delta t. So you can see we have del y, del z, del t. If we divide by delta x, delta y, delta z, delta t, then everything cancels and we get the delta x at the bottom. Likewise, if I collect the conduction terms, and there's a reason we're collecting them this way, which would be obvious in the next slide. So then minus k del t del x, that's this one, is here. And then minus k del t del x at x is here. And then the q term, everything gets dropped out. So it is left with just q. Okay. And now we take this control volume and kind of shrink it to 0. So delta x, delta t also goes to 0. So we shrink it to 0 and we also make delta t go to 0. So we get a differential equation. So the differential equation is simply the same equation, but now this finite differences would become derivative in the limit that delta x, delta t goes to 0, and then this is my heat equation. And we'll spend more time on what the terms mean. But so this we just derived for 1D. If we want to write the most general version, then it's the same equation, but the convection term, for example, written in vector form is del dot rho Cp u t, and then the conduction term is del dot k del t. So this is the most general version. Now you notice we didn't talk about where this velocity is coming from. That is going to be a separate module altogether, how we get the velocity. Basically, the velocity comes from the equations called Navier-Stokes equations, or their analogous equations that are separate from the discussion here. So that's where we get the velocities. So this heat equation that we derived with all the partial derivatives and so many terms can look daunting. But it would be much easier to handle this if we relate every time the terms to the physics that they represent, the physics of conduction, flow, generation, and storage. Each term represents them individually. So let's look at that. So the first term has change in temperature with time. So that must relate to the stored energy, because storing more energy changes its temperature, increases its temperature. So this rho Cp del t is the rate of change of stored energy in the control volume. Now the next term has velocity. So the details of velocity, as I said earlier, would be discussed later. For now, let's say the velocity is known, but the fact that there is velocity in the term, this must relate to the flow aspect, how energy is carried by flow. In fact, if you put in all the dimensions, you can clearly see that. I'm not getting into those details now, but this term then is the rate of change of energy in this control volume simply due to flow. Nothing, no conduction in there, just due to flow. So the energy flowing in and energy flowing out, their difference, and the time rate of that is what this term is. Then the third term, you see, has thermal conductivity. So that must relate to the thermal conduction. So what this term represents is rate of change of energy due to conduction in this control volume. Okay. Um, so the last one relates to rate of heat generation. So how heat is being generated in the control volume, and that is normally a conversion of energy from some other form into heat, like microwave heating. So if we look at this equation, do I need all of these terms all the time? By God, no. So we need this term if temperature is changing with time. It's an unsteady process. Otherwise, we don't need this term. We need this term if there is flow. But if it is just solid, then we don't need this term if there is nothing flowing through the solid. If the entire material is heated so uniformly, there is no temperature difference. So then del T del X is zero everywhere. Then this term would also be zero. That's very unusual, but it's possible. And then finally, if we do not have microwave heating, if we do not have evaporation, then this term would also get dropped. So we do not need all these terms all the time. I like to think of the equation that we derived with several different terms as kind of like the Swiss Army knife. Even though it has many different tools, that does not mean we need all of them all the time. Okay, so going back to the equation that we obtained by doing conservation of energy with heat conduction and flow, the equation is very general and it can be made even more general. So what do we mean by very general? We didn't choose a material. It's for any material, so which means it's for any food material. Then it's for any size or shape. And it is safe to start from this equation because it's the most general form. And so from there, we know as we drop terms, we know which physics we are ignoring and why. So we keep this relationship to reality that way. Now it can be made more general. The simplest one would be, let's say, if the thermal conductivity is changing or the properties are changing. So we need to write the equations in more general form. But nevertheless, it is this energy equation or some more generalized form of it that will describe for all different situations and where there's energy transfer is taking place or we need temperature solution. Just for completeness, here are the equations, the same equation in different coordinate system. We don't really need them in these details often when we are solving it numerically because these are already coded that way in the software, but still it's important to look at the form of the equations and also notice that to just make it not very messy on this slide, I have dropped the convection terms. Otherwise, each one of these will also have the convection term as we had derived. So then if we write in a very general form, vector form, so then our heat equation looks like this. And this is what it would look like when you are trying to use a software, because the software implements a very general version of the equation. Of course, there are limitations of the equations that we derived. And let's look at some of them. So one of them would be this thermal conductivity, for example, could be changing quite a bit as we are going to a high temperature process like canning. That's not a strictly speaking limitation of the equation in general, but of course it has to be written a little bit differently from what we saw, and we have to treat it carefully. We cannot always get analytical solutions for it. Then the boundary conditions. So to solve the equation for a solid, let's say, we need boundary condition here. But the boundary condition may not be easily available. In that case, one way to resolve it is we solve for the fluid and the solid simultaneously. And that's called a conjugate problem. Obviously, that gets to be more complex, but that's one way we can get around this kind of a simple formulation that we were showing. The most important one and the most common one where we would have difficulty with the equations as applied to food is in a complex system like bread baking or even simple drawing situations. We really have to think of multi-phase situations. So in this case, in the bread, we have solid, liquid water, and water vapor. So when we have these different phases, then we need some sort of averaging of the phases. This is discussed elsewhere. In fact, if we just go to a simple heating, like here, that we talked about thermal conductivity, so if it loses moisture, that also changes thermal conductivity. But if we have solid and liquid water, then we have to think of averaging. And then that kind of averaging or averaging for a multi-phase system is really discussed separately. This multi-phase transport thinking of food as porous media is discussed under separate modules, and the reader is referred to those modules for more details.